No longer at war, but in Karlsruhe.
Yeah.
And you've been talking about the gradient flows of things like Mobius energy and other O'Hara knot energies.
So it's a pleasure to be here and it's a pleasure to give this talk here. I'm speaking about knot energies, and I think we have heard plenty of things about knot energies. The questions I want to answer here is, well, somehow related to these things. So given such a nice or ugly shape of a knot, what is the nice representative of this knot? And how can we transform a given knot, sorry for the typo, into this representative? And we want to do that using knot energies. And the idea of behind knot energies is that we actually try to construct an energy that's blowing up whenever we try to leave such a knot class. So these squares are representing knot classes. So that's the content here, and that's the wrong thing. So that's the problem if you are not used to use your computer. So we have to actually construct such an energy, and the thing we want to prevent, so the thing that's preventing us to running out of this knot class is actually punishing self-intersections, and we use that using repulsive potentials. So that was an idea due to O'Hara, and well, we all know one repulsive potential, the Coulomb potential. So maybe it's a good idea to start with that one. So we start with a given curve, we look at 2 points, and we just make this ansatz. So take the double integral over some 1 over Euclidean distance to some power. Then we look at this ansatz, and actually O'Hara did that, and he wasn't convinced that this is going to work, because for the exponents we are going to use, this is going to be infinite. So we better subtract a term that makes it finite. And we subtract nearly the same term. We just exchange the Euclidean distance, the extrinsic distance, by a different distance, which is the intrinsic distance. So we just take the length of the shortest arc connecting our 2 points. And that's actually an ansatz that's working, and that's due to O'Hara. And again, thank you very much for your attention. Let's try to find the slide. What you have to keep in mind is the scaling, because the scaling of these energies is going to be extremely important. Of course, this integrand roughly scales like 1 over length of our curves to the alpha, and we get another length squared due to the integration. So it scales like L to the 2 minus alpha. And what you have to keep in mind is that it's scaling invariant exactly if alpha is equal to 2, and otherwise we have the phenomenon that when we increase a curve, the energy is going to decrease. So if it's scaling invariant, I will use a term that's a critical case, and the other case is going to be called subcritical, which is causing some confusion, because actually I call it subcritical if the exponent is too large. Then let's talk about whether these energies are doing what I promised you, and what we first have to show is that they actually punish self-intersections, or that they are going to be infinite whenever we have a self-intersection. And that's actually true, and was proved by O'Hara, if we assume that alpha is larger or equal to 2. Otherwise, these energies are not really good for our purpose. And well, we want to do some analysis afterwards, so it's good that actually we have some quantitative statement of that, which is much stronger than just preventing self-intersection. And this tells us that, of course, we can always bound the extrinsic distance, the Euclidean distance, by the length of the shortest arc. Actually, once we have a bound on the energy, we can get some bound in the other direction, so we can bound the intrinsic distance up to a constant by the extrinsic distance. And that's good for the analysis I want to do. That's the first big ingredient. So we can do at least one thing. So we have some self-repulsive effects. What about the existence of these nice shapes, the existence of minimizers? And well, if you look at all curves, the minimizers that was found out by Alperens, Cantor, Fu, and Gomi and Howard are the nicest curves, the round circles. Well, I'm cheating a bit. I told you before that these energies are not scaling invariant if alpha is different to 2, but in this case we just look at curves of fixed length, and then the statement is still true. One consequence of that is that actually we get an upper bound. So we have a lower bound on the index alpha. Below this bound we don't have self-repulsive effects. Now we get an upper bound because if alpha is larger or equal to 3, this statement can be used to show that actually these energies are infinite for all closed curves. The argument is just, okay, this theorem is still true, so the absolute minimizer is still the round curve, and you just calculate the energy for the round circle, and you get an infinite value. So that's the argument behind that. But that's not what we want to do. We don't want to minimize the curves, the energy among all curves, but we want to stay in fixed knot classes. And well, let's address this question. What about minimizers in given knot classes? And there we get the first distinction between critical and subcritical case. So if we are in the subcritical case, if alpha is between 2 and 3, so not for the Möbius energy, actually we have minimizers, and it's more complicated and a bit open in the case of the Möbius energies. It's just alpha being equal to 2. There we have a theorem if we are working in prime knots, or if we are working in prime knot classes, we have a minimizers, and otherwise it's conjectured that we don't have minimizers. It's a conjecture due to Kastner and Sullivan, and I think we have no idea how to prove that. Okay, so we have under some conditions minimizers, and now we can ask the question, how nice are the minimizers? And I'm an analyst, so I would phrase the question, are they smooth? And well, first this question was answered for the Möbius energy, for local minimizers in some topology, and in fact it was found by Friedman, He, and Wang, and He, that actually these things are smooth. And for the general cases, the theorem due to Philip Reiter was talking yesterday, that even stationary points for E alpha are smooth, but only under some extra conditions if we assume that we are in some strange space W alpha 2 already. And the question now is this the right space? Can we start with that? Do we get that for free if we assume that our curve we are looking at has finite energy? And in fact, that's not true, and that's the point where actually I started my work. So the first result of mine was that I classified the space of all curves with finite energy, and this can be done using some fractional Sobolev spaces. Of course, then we have a new question. So assume that we have finite energy, so we are in these strange function spaces. Are stationary points of these energies smooth? And first we proved that with Philip Reiter for the subcritical case, so for all except the Möbius energy. And afterwards we also could show that for the Möbius energy. So I could put that in one theorem, but I don't like to do that because actually proving the thing on the left-hand side is rather easy. The right-hand side is extremely difficult, maybe the most complicated paper I've written so far.
The result of her was the local minima.
Exactly. And that's the point where he had to use the Möbius invariance. And actually we cannot play this trick to get out of this critical regularity, to get some things out of this. And it actually gets quite hard. And let me just state that this is somehow related, and that's behind it. Somehow we find a connection between this Euler-Lagrange equation and the Euler-Lagrange equation. You end up looking if you are working with half-harmonic maps. But that's not really the topic of this talk. I promised you talk about gradient flows, so I have to bother you once with gradient. That's this ugly slide. You don't have to remember it. Actually, the first line is just a definition of gradient. So the first variation of this energy should be given by the gradient, which I denote by H alpha. And that's the formula. And I was very glad that I didn't have to compute it. Some people did it before. So again, Friedman here and Bang and Philip Reiter did that before. And what I really want to look at is at gradient flows, and these gradient flows should have some nice asymptotic behavior. For alpha being equal to 2, for the Möbius energy, I just look at the negative gradient flow. Actually, that's not going to work for the subcritical case for alpha being between 2 and 3, because they are not scaling invariant. So if I run the negative gradient flow, of course, because the energy is going to decrease when I increase my curve will just blow up and vanish to infinity in some sense. So how do I prevent that? An easy trick is just to add a positive multiple of the length to our energy and look at the negative gradient flow of that. And we will see that actually this is really nice. That's one thing, just adding a positive multiple. Of course, we can also look at the energy, but the gradient flow of the energy, but not on the space of all curves, but only on the space of curves with fixed lengths. This leads to roughly the same equation where now this positive constant lambda in the first equation is time dependent, and it has to be given by this formula. So what about results? Well, if we work with the subcritical exponents of alpha being between 2 and 3, something like that happens. So somehow the word is nice here. And actually that's also something I can prove. So if I'm looking at the subcritical case and you give me any, let's say, smooth curve, since the gradient flow does the job, it exists for all time, and it converges smoothly to a stationary point of a functional, well, and there's some subtlety behind it, so that it might be a slightly different functional than the functional I started with, because we had two flows essentially. In the first flow, our lambda was fixed. In the second flow, our lambda was time dependent, and I better take the lambda infinity, which is just the limit of our lambdas as the time goes to infinity. So that's the story for the subcritical case. Everything works out nicely. In the critical case, unfortunately, this life is much more difficult. And actually, if you run the gradient flow, something like that can happen. So I started with a simple composite knot, and we see that one of these knots pulls tight, and somehow the other one tries to pull tight as well. So we can run into trouble, but actually there are nice configurations where still life is nice. And that's a theorem I can prove, which is not too amazing, but it's a first start. So the theorem is just, if I know that I'm close to a local minimizer, then this flow behaves exactly how I expected. I have long time existence, and I flow back to a stationary point. It might not be the same one, because actually there are too many stationary points, but it is actually on the same energy level. And that's the content of this slide. But
do you expect the new critical point you get is a Möbius image of the first one?
I don't expect it. Actually, I don't expect it. I have no idea. Maybe that's true, but it would be too nice to be true, I would say. Okay, that's local minimizers are attractive, but of course we want to start our flow with curves where we don't immediately can guess what the nicest shape is. So we don't want to be close to the nicest shape, so we have to analyze the general flow. And the thing we want to do here is somehow look what's going to go wrong if actually the flow stops in finite time. And that's the content of this thing, and that's actually work in progress, and it states either the flow is going to exist for all time and behave somehow nicely, or we have some concentration effects. We have that, well, as we approach the time where it stops to exist, we can find a series of smaller and smaller balls, but still within these balls we have one quantum of energy, and that's complicated described on this slide. Well, this quantum of energy is this epsilon naught we can find on smaller and smaller balls. That's not allowed if we have smooth existence. If we have that, and I hope I can prove that, then we can do what we call blow-up analysis. So we can take these smaller and smaller balls, blow them up to a ball of fixed radius, and look what shape we end up. And I hope doing this analysis, at least for codimension 1, I can still prove that everything is nice. That, okay, if you have a plane curve, I conjecture that the gradient flow exists for all time and converges to a round circle. That would be great. And I'm really positive that I can prove that, but till now I was just stupid. So that's all I can do at the moment, or in the near future. What are questions we can raise? So actually, for the critical points, we have seen that some concentrations effects can take place. Maybe we can do something useful doing these. Maybe we can use them to decompose the flow, this is knot, into prime knots. Maybe, I don't know. The next thing we want to attack is, well, we have these energies, that was the content of this talk, but O'Hara actually invented a crater family. He also allowed an index P. And we have heard about tangent point energies and Menger curvatures. And we want to do somehow the same analysis for that, but let me state, and let me stop with that we have some problems with that, because in this case, for P being unequal to 1 and all these energies, the equations we are looking at will be degenerate, and I don't know how to deal with that. Yeah, thank you very much for your attention. So I do that one. Final time.
Any questions for Siva?
Could you put back your previous slides? Because your
Yes,
message is
sure.
very interesting. We want to meditate. Oh, yes, you have this problem. Yeah, this one, please. Thank you.
Sure.
And during questions, the next speaker help get set up. John. Yeah.
So you have examples where a prime knot under this flow for Möbius energy will concentrate.
Well, hopefully not, but it looks like the animation I showed is such a situation, but maybe it stops before. I would expect that it stops before, because it would be amazing if you have a prime knot that really pulls tight. I wouldn't expect that, but maybe, who knows?
Okay.
We
No,
know just too little.
I would hope, I would have the same hope as you.
Yeah.
I think you're showing it.
But either way, it would be amazing. Yeah?
Could you roll back like
Sure.
another slide to your conjecture?
This one? Also
Okay, so that means you ruled out other stationary points in our
Exactly. That's the point I can do. So actually, no, it's not cool, because for closed curves, this result was shown by Hare. But actually, you cannot have stationary points.
Oh, is this
plain
for the
stationary
Möbius
points.
energy?
It's just for the Möbius
Just for
energy.
the
It's just for
okay.
just for the critical case, just for the Möbius energy.
Okay.
Of course, it's not enough for our purpose, because we have to look at blow-ups. They might be non-compact. Actually, they are non-compact. One can prove that. So one has to extend this result by Q to A, but that's possible.
Thank you again.